Hello everyone, we are going to talk about a very important reaction today, that is SNNGP, which is called as substitution nucleophilic or nucleophilic substitution neighboring group participation. This reaction is a very important topic for various different competition exams. Mainly in advanced it is very important and it is very simple also. So basically the concept which is being applicable over here is very similar to SN2, or basically it's like extended SN2 and SN2 and SNI, the combination of both, and that is what is our neighboring group participation is. So as I said, this is a special case of nucleophilic substitution reactions. There are some important points which we'll discuss about SNNGP first, and then I'll tell you how it works. So this is the reaction which has a very fast rate of reaction, and this is unexpectedly fast rate of reaction. So basically it can be like 1000 and 10,000 times faster than a normal substitution reaction. So unexpectedly higher rate of reaction. Second thing, how to identify if a SNNGP is working in a particular condition or not. So on your beta position, on your gamma position, on your delta position, or any far off position in the chain, you should have some nucleophilic element present, or you can say you should have an element present which has unshared electron pairs which can act as a nucleophilic center. So that means on alpha position we will have a leaving group, and on any other position we will have one more group which can act as a nucleophile, which is like internal nucleophile. We have a nucleophile within the chain itself. Now, third thing is, we will see here that the reaction intermediate will have either 3, 4, 5 or 6 membered ring formation. So basically ring reaction will be feasible only if the intermediate formed is either 3 membered, 4 membered, 5 membered or 6 membered ring. Here what we'll observe is the retention of configuration ultimately, but again here do not generalize it. We will understand the basic concept here, and then depending upon case to case we will decide whether retention is happening or inversion is happening. So we will understand it logically. We will not just remember the retention of configuration. Now the last point is, smaller the ring as an intermediate ring which is forming, faster will be the reactivity. So out of 3, 4, 5, 6 membered rings, 3 membered ring is going to show the fastest rate of reaction. Now let me explain you the structure of SNNGP. Basically what kind of conditions it can be. You can have a carbon chain where you will have a leaving group present over here. This is your alpha position, this is your beta position, this is your gamma position, and you have another nucleophilic center over here, or you can say any element which is carrying a lone pair, and you have an external nucleophile also. So basically you can take it as an element with a lone pair. This is my element with a lone pair, okay, unshared lone pairs basically, which can participate in the reaction. And what we have is the nucleophile over here. So we have two things. We have a nucleophile, external nucleophile also. We have a delta positive charge on alpha carbon which is ready to make a bond, and we have an element which has electron density and which has a free shared pair of electron which can participate in the reaction. So this delta positive anyways wants the leaving group to leave, will not wait for the external nucleophile to come in. Instead, this element will first attack over here and kick out the leaving group, causing the formation of an intermediate state like this. Now we can see over here, this is a 4-membered ring which is forming. Once this 4-membered ring is formed, see, first of all you understand the attack which has happened from the element E on the delta positive carbon which is an alpha carbon, and leaving group went out. This is nothing else but a normal SN2 reaction, but in the internal circumstances. Basically within the molecule itself the SN2 is happening. So definitely when the first attack is happening, normally the way how SN2 gives you the inversion product, here the inversion will take place. Okay, so this is the normal SN2. There is nothing different we have done. Only thing is, in the SN2 which we generally talk about are the SN2s where the nucleophile comes from the external sources, and here my internal element itself is going to act as a nucleophile and attacking first, but the behavior of the reaction is same as SN2. Okay, so you can call it as internal SN2. Now once this intermediate is formed, obviously this is highly unstable intermediate because the ring chain is small size, and the nucleophile will come and attack on the carbon chain. So now I have a delta positive carbon over here and a delta positive carbon over here. I can have the attack on this carbon to push this electron density back, or I can have attack on that carbon and push the electron density back. So I have a pathway 1 or pathway 2. So two type of products which are possible. If I go by pathway 1, that is attacking on the carbon which is little far off having the extra branch, then what will happen? Then this will form like this. And if the attack happens according to the path 2, in that case this molecule will look like this. And in this case, again, what is happening? The attack is happening from the other side or the opposite side from where this E element is present. So again, one more time, an SN2 is happening from the external source, and again one more inversion is happening. So 2-time inversions means retention. So that is the reason why we say that in SNNGP the retention of the configuration takes place, and that is happening not for the reason that because the attack is happening from the same side. The inversion product is forming because 2 times the attack is happening and 2 times the SN2 type attack is happening, and hence first inversion is happening and then again second inversion is happening, which is ultimately causing the retention of the configuration. I'll explain you through some examples so that you can differentiate between the reactions properly. So the first reaction which you can see over here, we have CH3, CH2, CH2Cl. Only one leaving group is present, and we have a nucleophile that is OH minus. In this vicinity or on this alpha carbon there is a leaving group present, and around in the same molecule in the vicinity there is no other element is present which can act as a nucleophile or which has a lone pair, and hence OH minus will go attack on this carbon, will cause this chlorine to leave, and the reaction is simple SN2 reaction. This carbon is not an optically active carbon, hence we cannot talk about the optical activity. But if it would have been an optically active carbon, the inversion product would have formed. So this is simple SN2 reaction. Okay. Now let's alter the chain a little bit, and what we'll see over here is we have CH2, CH2, SPHCl. Out of sulfur and chlorine, definitely chlorine is a better leaving group. So this is my alpha, this is my beta, and on this beta position there is a sulfur present with a lone pair. Okay, and there is a delta positive charge. So definitely this S is gonna attack over here rather than waiting for OH minus to attack. If you see, the product will be still PHSCH2CH2OH, the ultimate product, but which mechanism it is going through, it is little different, and the reaction rate is much faster than an SN2 reaction, in fact 600 times faster. So what is happening? As I said, the sulfur is attacking on the carbon, that is alpha carbon, attacking internally first, causing the chlorine to leave and form the 3-membered cyclic transition state. This 3-membered cyclic transition state is so unstable that it will move to the next step reaction very fast. Now to just show you what kind of difference it can make in your product, I marked this carbon as a star carbon. So now I have got this 3-membered ring, and my OH minus has 2 situations to attack on, because I have a delta positive here also and I have a delta positive here also. So my OH minus can attack through pathway 1 and can attack through pathway 2, both. If it will attack through 1, then this carbon is gonna get OH and this star marked carbon is still intact at its place where it was. But if it attacks according to path 2, then what will happen? Then in that case, this carbon is gonna get the OH. Okay, the bond is gonna cleave from here, and this will look like PHCH2 CH2 star OH. So that means I don't have only one answer for this reaction, that is this. Assume if I mark this as star, this position as star, this is not the only answer we are getting. We are getting 2 different products. 2 different products only if I'm marking star. If I'm not marking star, then both are same. And so you can see, when we understand the concept properly or the pathway properly, it will be very neat and clean for you to understand how exactly the reaction is taking place. So this is how the product will form. Here both reactions are equally feasible, both products will form, and basically both products are same. But just in case, if I would have a chain where one carbon would be more sterically hindered than the other one, wherever the steric hindrance is less, the reaction will be faster there. So basically the external nucleophile will attack on that carbon only. For example, let me just show you one example now. So let's see this question. I have this question over here. In this question, you can see I have a nitrogen, I have a bromine, and I have aqueous KOH. Nitrogen acting as an internal nucleophile attacking on this carbon carrying a delta positive charge, causing the bromine to leave. Once the bromine will leave, there will be a bond formed over here. And this is how the cyclic transition state will form, which is a 3-membered cyclic state. Now when the OH minus will attack, where all it can attack? It can attack on this carbon, it can attack on this carbon, because these are the carbons with a delta positive charge, because nitrogen is withdrawing electron density towards itself. So if you see this carbon, this is more sterically hindered than the other one. So that means more sterically hindered means there are 2 pathways, pathway 1 and pathway 2. Pathway 2 is the better pathway for the reaction to happen. Why? Because it is less sterically hindered, and hence the product formed will be something like this. So I'll just write it here so that you understand more properly. So I have this. This is the compound. This my OH minus will come, will attack on this carbon and cause this bond to cleave. When this will cleave, my ultimately the molecule will look something like this, and the OH will attack over here. And this plus charge definitely we would have gotten rid of, and then we would have got a lone pair over here. So this is exactly what I have formed over here. So less sterically hindered carbon is going to get attacked by OH minus. Why? Again, the steric factor works over here because the reaction is ultimately nothing but SN2. It's just happening twice, that's all. One time internally, one time externally. But otherwise, the reaction is normal SN2 reaction. Now let's see a few more examples. So here again, I have a chain like this. Though I have written the question, but I'm still explaining you this by writing once again. This is my compound. Here, OTF, triflate ion. So in this compound, you can see tosylate group is the best leaving group, and here oxygen ka lone pair is going to act as the internal nucleophile, will attack on this delta positive carbon. In the arrow wrong, this is delta positive carbon, and this attack will happen over here. When this will happen over here, OTF is happy to leave. I have given this list to you, which are good leaving groups, which one are among the good leaving groups. So triflate ion is one of the good leaving groups. So it will leave nicely, happily, and your chain will look something like this. If you see here, this is how your chain is going to look like. Now, so let me just rub it off over here also so that you are able to relate. It will be, I think I have written something wrong. I had to write it like this. Again, I'm writing wrong. OTF. And also, the arrow of attack is somewhere here. Okay. So when this OTF will leave, then this will go out and the bond formation will happen over here. This is the new bond form. So this is how exactly your structure looks here. Now when the OH minus has to attack, let's say my OH minus is attacking, or OCH3 minus is attacking. There is a delta positive carbon over here. There is a plus charge over here definitely. And there is a delta positive charge over here. So OCH3 may attack here or OCH3 may attack there. This is pathway 1, this is pathway 2. Definitely pathway 1 is better because this carbon is less sterically hindered. So this bond will cleave on this carbon, OCH3 will come, and this OCH3 will regain its lone pair. So that's how exactly the reactions takes place. And this is pretty much the basic information about SNNGP. We will see few more examples to understand more different type of questions which can be asked from this part. Another example what we can see here is I have taken this molecule, okay beta, and the chlorine again is a good leaving group. So SH will attack internally through SN2 mechanism, and this is how the chain will look like. S will attack, will carry a positive charge. This is SH, and there will be H over here, and there will be H over here. Something like this will be formed. Now comes the OH minus. Now we can say that OH minus can attack on this delta positive and this delta positive on any of the position and can form OH, and SH will go back. This definitely is possible, but understand your OH minus can act as a base as well as nucleophile both. So what we will do here? Here you have an acidic hydrogen. S ke upar there is a positive charge, and hydrogen is an acidic hydrogen. So very high probability is there that this hydrogen will be taken away by the OH minus to form this molecule, this compound. So instead of second attack happening in such a way, so I'll just write it in a clean. So rather than this is my compound which I have formed just now, S and S with the plus and H, rather than my OH minus attacking on any of these delta positive carbons, it will happily take away the hydrogen. And what compound you're gonna get? This is what you're gonna get, which is why? Because acid-base reaction is fastest. Okay, so it's not like always the reaction will go this way. You have to put your brain over there. You have to think logically. And I have told you many times in the class that acid-base reaction is the fastest. So accordingly, reaction will take place. It's not always the external nucleophile which is coming and attacking will always kick away or will break the carbon and the nucleophile bond over here and it send it back. It will depend from situation to situation. Very similar question like that is the another one. So in this case also, if you see, it is a similar situation. Oxygen attacking on this carbon, chlorine going out. Once you got this, you have another OH minus in the system. OH minus, rather than attacking on this carbon, it will attack on this hydrogen, will basically take away this hydrogen, causing the formation of cyclic ether. In this case, especially, you must see, or not in this case, basically any of such reactions which we are doing, your nucleophile, which is in the same chain, not the external nucleophile, the nucleophilic element which is present on your carbon chain and the leaving group must be on the opposite planes, and that's how the attack would be possible and easy. If they're in the same plane, they may not be able to attack. I mean, basically, your internal nucleophile may not be able to attack to the carbon. The carbon which is carrying a delta positive charge, the carbon which is carrying the leaving group. So, this is also one of the important conditions, that your internal nucleophile and the leaving group must lie in the opposite plane. Now let's see this question. So in this question I have written CH3, CHBr and CHBr and CO minus. So abhi in this reaction, if I treat it with OH minus, it may feel like it is simple SN2 reaction. Br2 will get replaced by OH, but this and the inversion of the configuration will happen. The reaction is SN2. It's not exactly SN2. It's SN2 kind reaction, but inversion is not the product for this reaction. Let's understand how this reaction is happening. Again, this is your alpha position, and next carbon is basically beta. Okay. So on this you have a nucleophilic end. It will attack on this carbon and bromine will be kicked out. This is internal SN2 is what is happening over here. Once the internal SN2 is happening, first step is inversion. Your O is coming from the back side. Your bromine is going from the front side, and that is why the first product will be the inverted product. But again, we have an external nucleophile also, this is OH minus, which will attack from the front again and let the oxygen lone pair go back. So ultimately, when you see the formation of the compound will look same as what I had written earlier. Even if I would have done SN2 without having the knowledge of SN-NGP, I would have written the same product. But if somebody will ask me the optical activity, just considering that it is SN2, we may write inversion. But here what is happening? Retention. And why retention is happening? Because 2 times inversion has happened in the reaction. Now one more important question which I want to show you, which is very common also and which is very important also, and that is not only the elements carrying lone pair work over here, even benzene, which is electron rich species, also act as a nucleophile in these reactions. So I have taken the compound over here, which I am rewriting it here so that you can see the moves which I am doing here. This is my compound. Okay, beta. And now let's mark that this is a carbon 14. So let's star mark it so that we can understand and differentiate in the reaction what is happening. So definitely there is a delta positive charge. And what are these double bonds on a benzene? These are obviously nucleophilic areas. Okay. So what will happen is this electron density will shift on this carbon, and this carbon will attack on this carbon will attack on this carbon, causing the bromine to go out. And what will it look like? It will look something like this. So the electron density is shifting over there, and this is becoming CH2, CH2, and then 3-membered cyclic chain. There is gonna be a positive charge over here. Correct? Now aromaticity is broken. Cyclic 3-membered chain is formed, and the plus charge is there. Do you think it is a stable situation? Aromaticity broken is absolutely not a stable situation, and hence this particular intermediate would like to do the reaction faster, and that is why you would see aromatic compounds, when they participate in SN-NGP, their rate of reaction is much faster than an aliphatic chain. Now if a nucleophile will come, the nucleophile can attack on the 2 places. I had told you there is one carbon 14 over here, so this is my carbon 14. Let's mark it. Let's keep it in the circled manner. So nucleophile can attack over here and nucleophile can attack over here also. So this is pathway 1 and this is pathway 2. When we will do so, the species will look like this. If it is attacking on this circled carbon or star marked carbon, which is this, this is my star marked carbon. Your nucleophile is gonna attack here and this bond is gonna cleave there. When that will happen, your molecule will look like this. CH2, CH2 star and the nucleophile. Correct? Now, let's suppose I assume that the attack is happening other way around and it is attacking on this carbon. So this bond will go over here and the molecule will look like this. So if you understand, there is a difference in the compound formed here and the compound formed over here. So if somebody will ask me how many products are possible, obviously these 2 different forms are possible, and obviously If there is a chirality, then you will have to include the stereoisomers also. But these two products are possible because it's not simple SN2, but SN-NGP is happening. So SN-NGP may not have a very strong significance with respect to the product change. Product will remain same many a times, but your optical activity will differ. And hence we have to very carefully see whether in my chain there is only one nucleophilic element, or you can say leaving group, or electron rich center, or we have more than one electron rich center. If more than one, then SN-NGP is gonna happen. Rather than external nucleophile attack first, the internal one will attack first, and then in the second step, the external nucleophile will attack. So this is all about SN-NGP. Now you can solve all the questions what you have seen so far and which I had told you not to solve unless I explain you. You can start solving them. There is no other question which can be asked beyond this what I have explained you. So apply what has been taught and try solving it. Thank you.